Okay, let's dive straight into mastering one of the most notoriously misunderstood topics in the entire Cambridge Computer Science syllabus. Welcome to the Explainer. Listen, today we are treating your upcoming computer science exam exactly like a high-stakes operation. Think Ocean's 11, right? Pulling off the perfect heist requires a brilliantly designed blueprint, a highly specialized team of cognitive experts, and flawless execution when you're under pressure. Your ultimate target today? Securing maximum marks on those tricky scenario questions regarding temperature, pressure, infrared, and sound sensors. Whether you are studying syllabus 0417, 0478, 0983, 0984, 2210, or tackling the advanced 9618, these questions are the vault, and today I am giving you the exact combination code to crack it wide open. We're going to completely overhaul how you look at exam papers.
So you might be wondering, why do so many smart students consistently lose marks on sensor questions? Examiners constantly report that students struggle to apply core concepts to unfamiliar contexts. Look at the split-screen scenario we've set up for you here, taken directly from a real Cambridge Computer Science past paper, specifically a classic-style question you'd see in code 9713 or 9618. On the left, we have Alex. Now, Alex is the classic overpreparer. He overloads his answers with raw, unfiltered computer science facts. If you ask Alex about a temperature sensor, you are going to get a massive, textbook-perfect definition of thermistors, resistance levels, and analog signals. But guess what? There is absolutely zero analysis of the actual system context. Result? Red ink everywhere. A massive block of text, but practically zero marks. On the right, we have Sam. Sam's problem is entirely different. Sam rushes the paper, completely misses the specific command word requirements, and ends up answering a complex describe question with a simple one-word state bullet point. Result? Valuable marks left sitting on the table. Both of these students actually have the foundational knowledge, but neither is cracking the vault because they lack the strategy.
So, to fix this, here is our strategic roadmap for today's session. We are going to expose the root disconnect in student answers when it comes to hardware and sensors. Then, we'll decode exactly what the grading room is searching for behind the scenes. We're going to build a bulletproof procedural framework so you never freeze up. We'll sharpen your algorithmic problem-solving skills for those high-mark programming questions. We'll look at the top 3 explicit warnings from examiners. And finally, we're going to secure your ultimate safety net with the Method Mark Lifeline. It's a packed agenda, so let's get right to it.
Let's start with the first phase, the sensor problem revealed. We need to look at exactly what examiners are searching for and why standard rote memorization just isn't enough anymore. The fundamental disconnect happens because in Cambridge Computer Science, a sensor is literally never just a sensor. It's a bridge. It is the crucial translation point between the physical, messy, continuous analog world and the structured, digital, discrete binary world. When you are given a scenario about an infrared sensor in an automated supermarket door system, just dumping facts about how infrared light waves work isn't the key. The examiner doesn't want a physics lesson. They want to see if you understand how that physical data becomes a computational variable.
This quote directly from the principal examiner reports highlights something crucial. It shows that simply knowing what a temperature or pressure sensor is won't get you top marks if you lack the structured reasoning to apply it to a system. The reports consistently flag this exact issue year after year. The theoretical architecture of these sensors rests on precise definitions, sure, but way more importantly, it rests on causal relationships. How exactly does the pressure sensor trigger the analog-to-digital converter? How does the microprocessor continuously pull that digital data and compare it against a preset threshold stored in memory? If you can't logically connect the physical hardware to the software algorithm, you are going to lose the marks. It's that simple.
And this brilliantly illustrates the difference between our two students. The Cambridge Assessment Framework strictly prioritizes analytical depth and cross-topic connections over just listing superficial facts. Alex's approach was all superficial breadth, throwing every single technical fact at the wall and hoping the examiner gives a mark for one of them. Sam's approach lacked depth entirely. To achieve true analytical depth, you need to structure your answers like a professional. This is where top-tier students deploy the PEEL framework: point, evidence, explanation, and link. You make your technical point, you provide evidence from the specific sensor scenario given in the paper, you explain the computational process behind it, and you link it back to the system's ultimate goal.
Moving into our second phase, decoding assessment objectives. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's get back to unlocking this vault. The vault isn't unlocked by raw knowledge alone. It's unlocked by demonstrating specific cognitive skills dictated by the exam's command words.
If you don't understand the command words, you are essentially trying to pick a lock with a wet noodle. When a question says evaluate the use of a sound sensor, it requires an entirely different cognitive domain than a question that simply says identify a suitable sensor. Identify is just a quick grab. Evaluate means you need to weigh the pros, the cons, the system context, and make a justified conclusion. To achieve those top marks, your answers absolutely must hit all three of these domains, proving not just theoretical knowledge, but practical application and rigorous data analysis. AO1 is knowledge and understanding. That's knowing the ADC converts the signal. Simple enough. AO2 is application. That's explaining how a specific 8-bit register handles that converted data in, say, a greenhouse temperature control system. AO3 is analysis. That is critically comparing whether a continuous polling loop or an interrupt-driven method is more computationally efficient for that specific greenhouse setup. You have to layer these skills.
So, how do we layer them under pressure? That brings us to Phase 3, the procedural framework strategy. To consistently hit those assessment objectives, we need a bulletproof procedural framework for tackling any complex sensor question they throw at us. We are going to transform those red pen marks on Alex and Sam's papers into green check marks right now. We need an answering system that works every single time, whether the exam gives you a nuclear reactor temperature sensor, a robotic vacuum infrared sensor, or a burglar alarm sound sensor. The context changes, but the heist blueprint stays exactly the same. This procedural sequence you see here is your algorithmic approach to problem solving. It ensures you systematically transition from identifying key elements to verifying your results. Let's do a live mental rewrite for Alex and watch the red pen turn to green. I want you to imagine a 6-mark question about a greenhouse control system. We're putting 60 seconds on the clock for this rewrite attempt. Step 1. Deconstruct the command word. It's describe. Step 2. Extract data. It uses temperature and pressure sensors. Step 3. Analytical framework. We deploy the Peel method. Step 4 and 5. Execute and present with terminology. Instead of Alex's vague dump of textbook facts, the new answer reads, the temperature sensor captures continuous analog data from the greenhouse environment. This analog signal is sent to an analog-to-digital converter to become discrete binary data. The microprocessor continuously compares this digital value against a preset threshold stored in memory. If the value exceeds the threshold, the microprocessor sends a signal to an actuator to open the windows. Boom! That is exactly how you secure full marks.
Furthermore, when executing your analysis, your data interpretation skills must be razor-sharp, particularly when extracting binary representations and calculating evidence-based conclusions. You might literally be given a diagram of an 8-bit binary register showing the output of a pressure sensor. You need to confidently translate that binary to denary, calculate if it meets the system's pre-programmed boundary, and logically deduce the next physical state of the system. Does the door open? Does the alarm sound? You have to be the microprocessor.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's dive into Phase 4, algorithmic problem solving. We are stepping into our interactive workshop. I want you to look at the complex raw data grid on your screen. This represents data from an infrared sensor over a 60-second span. You have 60 seconds starting now. Your challenge is data scan. You aren't just looking for random numbers. You are extracting the core trend. Look closely at the values. When does that digital value suddenly drop to 0? What does that represent physically in the real world? It represents a physical object breaking the infrared beam. Understanding that connection, that is algorithmic problem solving in action.
Whether dealing with infrared or sound sensors, you must decompose the problem step by step, implement efficient code, and critically evaluate time and space complexity. If you are asked to write pseudocode for a sound sensor burglar alarm, you have to select the appropriate data structure to store your threshold variable. You have to write an efficient loop that continuously pulls the sensor, or, if you want top marks, implement an interrupt service routine so you aren't wasting CPU cycles. Examiners are specifically looking to see if you test for extreme conditions and if you evaluate the actual performance of the algorithm you just wrote. Now, higher-order assessment questions will ask you to compare approaches, which requires you to clearly identify both similarities and differences backed with justified recommendations. For example, comparing a pressure sensor pad at a secure door versus an infrared motion sensor. If the command word is compare, you absolutely must use comparative connectives. You must write something like, an infrared sensor detects motion across a wide, continuous area, whereas a pressure sensor requires direct, physical, localized contact. Without the word whereas or however, you haven't actually compared them. You've just stated two independent facts and you will lose the comparison mark.
So we have the framework, but let's look at the insider intel from the principal examiner reports on where students unexpectedly lose marks. It's time for Challenge 2, Find the Flaw. I'm going to read a sample paragraph, and I want you to mentally identify the sentence that is losing marks. Here we go. The temperature sensor measures the heat in the room. It sends this data to the microprocessor. The microprocessor then turns on the air conditioning. Okay, time's up. Did you spot the flaws? There are multiple. First, we are missing the ADC conversion. Microprocessors can't read raw heat. Second, we are completely missing the comparison to a preset threshold. And third, and most importantly, we are missing the actuator. A microprocessor is a silicon chip. It cannot physically turn on a mechanical air conditioner without sending a digital signal to an actuator. That paragraph would score maybe 1 out of 4 marks.
This transitions us perfectly into Phase 5, Top 3 Examiner Warnings. Examiners have explicitly highlighted 3 recurring errors in student responses regarding sensor technology across all Cambridge syllabuses. Let's make sure you never make these mistakes on your paper, setting you up for Challenge 3, Speed Writing Perfect Responses.
The crucial point here is to avoid these traps at all costs. Provide specific technical details, explicitly test your edge cases, and tightly tie your answer to the scenario provided. Mistake 1. Vague answers. Saying the sensor checks the temperature gets 0 marks. Saying the sensor captures continuous analog data, that gets a mark. Mistake 2. Boundary conditions. This is huge in programming questions. If a pressure sensor alarm triggers at 50 kilograms, what exactly happens in your code at 49.9 kilograms? More importantly, what happens at exactly 50.0 kilograms? Does it trigger using a greater than operator or a greater than or equal to operator? Your algorithms must explicitly account for these edge cases. Mistake 3. Context drift. If the exam paper is specifically about a sound sensor and a baby monitor, do not start talking about infrared sensors in a supermarket door just because you memorized that past paper. Anchor every single sentence to the baby monitor.
So, we've covered how to write the perfect answer. But what happens when things go wrong? How do you save your grade when your final calculation or final answer is completely wrong? This brings us to the ultimate safety net for your exams, Phase 6. This is a strategy that can literally salvage your score. When you're under pressure, let's say you're doing a complex 6-mark calculation involving binary threshold data from a pressure sensor. Your brain freezes, the clock is ticking, and you miscalculate the binary to denary conversion. Is all lost? Do you score 0? Absolutely not. Even if your math is wrong, you can save your score by documenting perfect algorithmic steps. Welcome to the Method Mark Lifeline. Let's uncover the grading room secret that actively rewards your computational process over your final output. This is the exact difference between a student who panics, leaves a blank space, and loses a grade boundary versus a strategist who steals points right out from under the examiner's nose even when they make a mistake. The method mark strategy dictates that examiners will award marks for your systematic processing. Therefore, you must always document your clear notation and algorithmic steps. Think of it as your exam insurance policy, as brilliantly illustrated here. If you clearly document your step-by-step decomposition, showing exactly how the analog data from the sound sensor should be converted, how it's processed in the registers, evaluated against the threshold variable, and used to trigger an actuator, you will pick up the majority of the method marks. You are proving to the examiner that you possess the analytical depth and algorithmic thinking required by the syllabus, even if a minor arithmetic error occurred at the very end. Your working out is your safety net. Never just write the final answer. By shifting from rote memorization to this structured, procedural framework, you are now perfectly aligned with the examiner's blueprint. Let's recap the complete system that guarantees top marks. Rule 1, command word decoding. Know exactly what cognitive domain you are being tested on. Rule 2, Peel framework application. Structure your analytical depth so you don't end up like Alex or Sam. Rule 3, the time management matrix. Don't rush and don't overwrite. You now have the complete blueprint to crack the vault. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.